So, next we come to the idea of what is called normal subgroup or invariant subgroup, both terms are used. This is the subgroup H, or let us call it N, such that its left cosets and right cosets are exactly same. A subgroup N such that its left cosets and right cosets are the same as sets. So, each set in the list of left cosets has a corresponding member from the right coset list, so that they are identical sets. So, as sets they are identical. So, a subgroup N such that its left coset and right cosets are the same is called normal or invariant subgroup. I think we will use invariant subgroup. It is easy to quick to remember what it means. So, i.e. we can say Gn equal to Ng for any G in the for all G belonging to G. What this means is that G n G ni G is equal to some G inverse, I am sorry, G ni G inverse is some Nj for all G belonging to G and for given Ni Nj belonging to N. So, if you pick some element of the normal subgroup and take any element of G, do G and G inverse, you will get back element in the subgroup itself. So, this is called normal subgroup. So, we will see examples of this a little later. We can try to see an example of this coset space. In fact, the simplest example we have, we will automatically get a normal subgroup. So, let us see an example just to understand what is going on. So, suppose we have C8, okay. This is 8-fold rotations by 2 pi by 8. Or in other words, have an octagon, the symmetry group of the octagon. But ignoring reflections and other things, okay. This has a subgroup which is say C4. Which is what we already saw, right, pi by 2 rotations. Now suppose we take some element of C8 and multiply on the left by this. Where I take e to the I pi by 2 and multiply on the left. What will I get? I will get e to the I pi by 2, then this will become e to the I pi, this becomes e to the 3 I pi by 2, and I get identity here, well 1 in this case we write, it is number 1, numeral 1, right. So this is one left coset, but because there is 2 pi n by 8, I also have 2 pi by 2n pi by 8, which is so I should have 45-degree rotation as well, right. So if I have e raised to I times I pi by 4 times C4, then I get something else. I get e raised to I pi by 4, that is 2 I pi by 8 of course, but now I will just get e raised to 3 I pi by 4, e raised to 5 I pi by 4, and so you can draw an octagon and check what is happening. This is rotating it by pi by 2, and then this is smaller rotation. This is just to demonstrate that if I take distinct elements of G, I may get distinct cosets, but the length of the coset, size of the cosets is the same, has to be the same, and they are all with distinct elements in it. Now clearly the order of C8 is 8 and the order of C4 is 4. The fraction we get is 2. And so we expect two distinct left cosets. And in fact we have exhausted both of them here. If you now take anything else, so we took I pi by 4 and we took I pi by 2. Suppose you took 3 I pi by 4, okay. What is going to happen? The first element will become 3 I pi, we left multiply the subgroup by that. So 3 I pi by 4 here, this will become 5 I pi by 4, 7 I pi by 4 and I pi by 4 again. So basically you will repeat this list. So if you take any other element from the group G, you are basically just going to repeat either one of this or this. So we see that we exactly get two cosets that are independently the cosets of this particular subgroup C4. You could have played the game the other way around. Suppose we pick this subgroup only 1 and minus 1, because in the list of C8, 1 as well as minus 1 are there. Now I have a subgroup of order 2. If I start multiplying from the left, I will get 4 different cosets, because I had only 1 and minus 1. If I multiply by say I pi by 4, it will become the I pi by 4 line, I pi by 2 line, 3 I pi by 4 line, but that is all. You will get 4 different sets. In other words, it will be 8 divided by 2 equal to 4. But you see that once you have a subgroup, its left cosets will form, the size of the left cosets is exactly a divisor of the whole group. Now because this group also happens to be abelian group. So it also happens that the subgroup is invariant subgroup, because for an abelian group, any subgroup is automatically normal or invariant. Why? Because need to check the condition that G H1 G inverse has to be equal to H2, right. This is the condition to be satisfied by Hi belonging to H for any G. But this is always true because H1 and G inverse commute. It is an abelian group. So, I can always bring G inverse to this side. So, in fact, it leaves H1 H1. For an abelian group. So, this can be checked in this particular case. Well, it is rather trivial because they are just complex numbers, whether you left multiplied or right multiplied, it is going to be the same answer. So, the left cosets are going to be same as right cosets. So, for an abelian group, all the subgroups are automatically invariant or normal subgroups. Okay. So, this is a property of groups which we will be using later. Okay. So, any questions so far? All right. So, then we do a few more things about the permutation group. And let us see, we can prove one important theorem. So, now we go to the notion of theory of permutation groups, and we will see a few interesting things in it, and hopefully if we cover all the required things, then prove one interesting theorem. So, let us start by saying representing, so finite groups as subgroups of Sn for some n. Given any finite group, what we are now trying to show is that actually it is a subgroup of Sn. Okay. First, we can show that we can write out the elements of any finite group as a permutation. Okay, so the first statement is we can realize it as a set of permutations. Note the word I am using, realize. We had said last time that you can have an abstract group which is just specified by some table, and when you produce an example of it, you say that you have a realization of the group, where you supply some set of objects on which operations can be carried out, and then you check that the operations carried out obey the multiplication rule given in the table, then you have a realization of the group. So suppose somebody hands you a multiplication table, where I have, we have been writing like this, and we have some E, and how shall we label the things, A, B something, A, B, C. Okay. Suppose we take one particular row in this. Now, what does this row represent? It is equivalent to this element B acting on this top initial row of elements. That is what this row is producing. So we can write a permutation pi corresponding to B like this. In the notation we introduced last time, right, we introduced this notation for permutation group, that we write a top row and then write the effect that the permutation has in the second row. So we can represent the element B like this. Thus all, and remember that each of the, in this row, all of this element, this relies on the fact that it very crucially relies on the group properties, that the group multiplication gives unique answers. You can't have AB equal to C and AF also equal to C. So the effect of B multiplication here is exactly just a permutation, right, of the elements of this. So thus, for a group of order n, there are elements pi g of Sn which realize, so group G of order n which realize G as permutations. So this looks like a clever trick, and what one has to remember is that n is some number, but Sn, its whole size is n factorial. So Sn is a gigantic group, but by paying the heavy price of considering members of some huge group, you at least represent any possible group of size n as some permutation. So every possible finite group can be realized as a subgroup of Sn, where n is the order of the original group. So firstly I have said, okay, so far I actually said subset, right, because all I proved to you that there exists an element in Sn for every element of G. Now we have to check the group property. Okay, that it actually forms a subgroup of Sn needs to be proved. There is a map from any group of group G of order into Sn. So we have verified that there will exist some element in Sn which will realize whatever and G does. But now we need to check that it actually forms a subgroup when realized as a permutation. Okay. To check the multiplication rule, multiplication is also realized So what do we need to do? So suppose we realize pi b and pi c, because we are going to use A1s here. So let pi b be equal to, and what we will write is simply some sequence A1, A2, An. Okay. We have been writing 1, 2, 3, 4 numerals, but you can just write instead A1, A2, An, and you will see that why we want to keep this a little abstract. Obviously, pi b is realized by whatever is the effect of b on A1, whatever is the effect of b on A2, etc. So this representation gives you how pi b is represented as a permutation, and let pi c be equal to A1, A2 dot dot An with CA1, CA2, CAN. Now how are we going to compose the two? Well, so also note pi for C times B is going to be equal to A1, A2, An with C times B acting on A1, C times B acting on A2, etc. Okay. Let us check that pi Cb is same as pi. So in group theory we have to remember to write it like this. Okay, it's pi C, so C will act first, then B will act. So pi Cb we should have no, so we have to multiply pi C times pi B, I'm sorry. Same order as this. So B will have to act first and then C, then we should reproduce the action of Cb on this. Now to do this we have to use the trick we had introduced last time for multiplication of permutations. So to calculate pi C times pi B, we will write pi C in the form BA1, BA2, etc. Suppose I write the top row like this, then by our rules of representation, it means that the lower row will be equal to C BA1, C BA2, etc. Right? It's the same permutation as pi C written here. So this pi C, what I do is I multiply the top row by B, but do the same thing to the bottom. Then the permutation has remained the same. So this represents pi C as much as this, and times I write pi B as before, which is here, but here I have BA1, BA2, BAN. Now remember the rule we had made that if you can rearrange things like this, where the bottom row of right element is same as top row of the left element, we can quote cancel these two like we would like to do in high school, and so it reproduces an times C B A1, and now because of associativity, C on BA1 is same as CB on A1, etc. Right. So this is same as our pi CB, right? It's exactly the same thing. So one can reproduce the entire group property of any finite group by realizing it as a set of permutations and then carrying out multiplications as you would do for any permutation. So thus of order n, this is very crucial, of order n is realized as a subgroup of Sn, the permutation group Sn, which is a huge group. It has n factorial elements, whereas our G had only n elements, but we managed to represent it. Okay. So this is a very important thing to know, because you do not have to struggle, you do not have to worry. So if we had just said that a group means a multiplication table that obeys associativity, that's all you can say, right? And closure, that every element is somehow produces a unique product and its inverse exists. So I have a table. You might worry that at order n, I might have some very large number of groups, and whether I have listed them all and so on. But now the point is that every possible group at order n is going to be some subgroup of pi n, of the Sn, and therefore some of the properties will be anyway inherited from Sn as well. So this is a very reassuring thing, and this is called Cayley's theorem. Okay. So I think we have seen quite a few generalities of groups and subgroups, normal subgroup. So we will end today by saying a few more things about permutation groups, which is, yeah. So one thing is about, so we are now actually going, so far we said something very general about finite groups and that they are subgroups of the permutation group. But now we go on to say some things about permutation groups themselves. Well, they are also called symmetric groups. What is transposition? If I just exchange two elements in a set of n elements, if we exchange any two, we call this transposition operation belonging to God, to Sn. Right. If we exchange, it's a permutation. This, but it is an operation on the n elements, This we call a transposition. Our claim now is that transpositions generate all possible permutations. Okay. Given any permutation, I can break it up into a series of transpositions. And therefore, the set of transpositions which how many elements do we have? NC2, right? I have to choose any pair. So, the NC2 transpositions generate all the n factorial elements of the Sn. And as you know, NC2 is n factorial divided by 2, NC2 formula gives you a number smaller than n factorial, and that produces n factorial. The transpositions Z generate Sn. Because if you can think of any permutation, you can do it in sequence of exchanging pairs. Now, given a particular permutation, if you start exchanging, you might sometimes end up taking a longer route. You may do something back and forth once in a while. You could have taken a shorter set of permutations. But the number of permutations you will take to reach a given number of transpositions you will take to reach a particular permutation will be either odd or even, and that number will, that oddness or evenness will remain the same regardless of if you do some redundant transpositions. Pi belonging to Sn can be obtained as odd number of transpositions it is called odd permutation. And likewise even permutation. Note that if there are redundant transpositions you ended up making, they will always be even in number. So, oddness and evenness will remain the same. From this, we arrive at one interesting subclass of the Sn group. So, if we do not do any permutation at all, we treat it as even permutation because there is no exchanges. admitting identity permutation to be even, we see that the subset of even permutations forms a subgroup. Right, because product of two even permutations is always even, that you can check because of the number of transpositions involved remains even, but product of two odd permutations becomes even because odd plus odd is an even number, and therefore product of two odd permutations does not generate an odd permutation, but product of two even permutations does, and we include identity in that list. So then the even permutations generate a subgroup. Do not, because they lack closure. Odd into odd is even. But even into even remains even, and we include the identity element. So certainly this is true. Inverse is not so much of a problem. An odd permutation, the inverse would also be odd, but the closure itself is not realized. So the odd ones do not, but the even ones by themselves form a subgroup. This subgroup is sometimes called AN. Why sometimes? I mean, this is the standard terminology. AN, again through some strange reason called the alternating group. AN. So even permutations of a set of size n forms also a group. It is called AN, and it is one of the biggest subgroups of Sn. It has how many elements? N factorial by 2. Okay. The next idea is the idea of cycles, which let me just introduce and then we will continue next time. So you have a set of elements, but what we are talking about the operation on the elements, right? So if I have a particular order and then they appear in another order, how many things did I have to exchange to get from here to there? So we can see, okay, good. So there is we can see an example. So we can try to check. Suppose I have something like this 1, 2, 3, 4, 5 elements, and that they become 3, 4, 1, 2, and what is it, 5. Okay. This is an element of S5, right? Now, can we obtain this as a series of permutations? Okay, what did you say? 1, 3, what was your order? Then according to our rules of representing permutations, we are supposed to write this out as like this. Whatever is below 3 goes here, whatever is below 2 goes here, whatever is below 4 goes here, and whatever is below this. These are both same. So it doesn't matter what order you started with, but what you are going to perform on it, how many operations. This is the statement about realizing a group. There is a base space or a carrier space, and there are operations on that carrier space. We have this little square or octagon, and we are rotating it. So we could have already rotated A, B, C, D into something D, C, E, F, G, but the operation of pi by 2 rotation will still remain pi by 2 rotation. So we can check two things here. I mean, does anyone doubt that this can be represented as set of permutations, as transpositions, pairwise exchanges? How will we get from this to this? So if I take, so 3 and 1 are of course pairwise. Actually the way it is written, it is already of the form 1 and 3 are exchanged and 2 and 4 are exchanged and 5 is not exchanged. 5 remains 5. So this is a pairwise exchange representation of that same permutation. But now we are writing it like this. This is a notation in which, this is a different notation in which 1 goes to 3, 2 goes to 4. Suppose we take the group of permutation of just 3 elements, okay. Consider S3. We know that we get 1, 2, 3. The cyclic permutations are 3, 1, 2 and 2, 3, 1. And then there are so-called anti-cyclic permutations. So, which is in which I transpose only 2 and 1 and leave this unchanged. And then I do cyclic permutations of this. Now we have exhausted all the 6 elements of S3. So if I have 3, I have 3 factorial elements in S3. There are 6 of them, and I have, so ideally I could write out this as one permutation. Then I could take this same starting and write this as the second row and so on. So these are all the 6 possible permutations. So these are the representations of the objects, not the representation of permutation. I have to write out permutation for each of them, which would take long, but you know what this means, right? So these are list of permutations, list of permuted order. Is like this. So I have 6 elements in S3 and they are essentially going like this. Now we can see that this permutation, the 2, 1, 3 is essentially one exchange, right? So it is an odd permutation. So this is odd. Then if I go to 3, 1, 2, I can get 3, 1, 2 by first exchanging 1 and 2, so that 1 comes here, but 2 is here. Now I exchange 2 and 3, so I will get 3, 1, 2. So this is an even permutation. We can check that this is also an even permutation because I can exchange 3 and 1 first, which will bring 1 here and 3 here, and then I exchange 3 and 2. So again there are 2 permutations, it is even. Suppose there is a long list which you have to exchange. You might exchange and then reverse the exchange. So you might end up doing some redundant exchanges, but those exchanges will always be even in number. You will be doing something which was not really required and then undoing it. So it will always remain like this. So these are all even, and we of course leave the original order, nothing has happened to it, as even, and these are all odd. So the set of cyclic permutations, so these we sometimes call in physics, sometimes these are called anti-cyclic, but this is a strictly physics terminology, and these are called cyclic order. The cyclic order permutations will form a subgroup A3, okay, whereas these don't. The other thing, so we will continue next time.